Hello students, welcome back to yet another session in unit number 4, that is psychrometric chart. Now we are going to discuss about psychrometric chart, and it is very important chart in HVAC systems and also air conditioning systems, refrigeration systems. We are going to discuss how to use psychrometric chart which is available, and this chart in our library, central library, we have many copies. You please borrow copy from library and see, and it will be very useful to our syllabus. So these are the topics we have seen so far, and now we are going to see and complete psychrometric chart. Psychrometric chart, and then we have psychrometric of air conditioning processes, and then mixing of air streams. So these are the two more topics left out in this unit that we will discuss in subsequent sessions. So we will see the psychrometric chart and how to use it for computations, and we will see numerical problems on this. So psychrometric chart, all data essential for complete thermodynamic and psychrometric analysis of air conditioning process can be summarized in a psychrometric chart. So that is the psychrometric chart where we can get all the information, and complete thermodynamic psychrometric analysis can be done using this psychrometric chart, and which is essentially to this system, that is air conditioning processes. At present, many forms of psychrometric charts are in use, so there are many forms are available, and the most commonly used chart is omega T chart. So that is the chart with the specific humidity, that is omega, and water vapor pressure along with ordinate, that is y-axis. So next on x-axis we have T, that is dry bulb temperature, along the abscissa, that is x-axis. So along x-axis we have dry bulb temperature T, and along y-axis we have water vapor pressure or specific humidity. It is also called as specific humidity. The chart is normally constructed for a standard atmospheric pressure of 760 millimeter of Hg or 1.01325 bar. So normally this is the standard atmospheric pressure considered in this chart. This corresponds to mean sea level atmospheric pressure. So coming back to the psychrometric chart, constant property lines on psychrometric chart. Now we will see the constant property lines. So this is the chart, and on x-axis we have dry bulb temperature, and we have wet bulb temperature, which is a line inclined to dry bulb temperature. So these are the parallel lines, and we have specific humidity omega, and water vapor pressure, so that is on y axis. So these are the two parameters. Now this line is known as saturation line. So this line is very important, where the humidity is 100%. So after that it cannot absorb any water content, because the saturation state reached with this curve. So this separation line, the saturation line separates the both the states where it cannot take or it cannot absorb any more water from here. And now this is the point of intersection, where we have specific humidity and dry bulb temperature. So from this point of intersection we can find out this dew point. So this is the wet bulb temperature, and dew point temperature can be find out on saturation line. And there will be another scale here which is not shown in this, so that is known as enthalpy scale. So heat contained by the air So that is the enthalpy scale, so that is almost parallel to this saturation line. So that is not shown here, but if you see the actual psychrometric chart, you can find that also. So this is the volume, specific volume, and this is the dry bulb temperature, constant dry bulb temperature, and this is the constant specific humidity line. So this point of intersection is between the dry bulb temperature as well as specific humidity. So from here we can find out graphically the many parameters. So if we know any two parameters, we can find out many other parameters. So saturation line, so that is the saturation line, we have dry bulb temperature line, and then the specific humidity lines. So this is a specific humidity line, and the relative humidity, so this is a relative humidity line. So the relative humidity is normally prescribed in terms of percentage, and the wet bulb temperature, and this is the wet bulb temperature lines, and dew point temperature, so this is dew point temperature. Enthalpy line, actually it is not shown here, and we have enthalpy line here. So from this dew point we can extend to enthalpy line, and we can measure enthalpy also. So these are the lines, important lines in psychrometric chart. So if you see the actual psychrometric chart, it will be very complex to see. It is very complex, but when you start using that, it will be a very simple chart, very simple chart. You will have to find the point of intersection of any two parameters, and with that we can find other parameters very easily in that chart. So it is very easy to find other parameters also. So coming to saturation line, so this is the saturation line represent the states of saturated air at different temperatures. An example of saturated air at a 20 degree Celsius, and we have to find this from steam tables. So where vapor pressure of water at 20 degrees Celsius from steam tables, PS equal to PV, so that is equal to 17.54. So this value you have to find from steam tables, and mm of Hg, it is 2342 Newton per meter square. So total pressure we can find from steam tables, it is 101325 Newton per meter square, and the partial pressure of dry air we can find out P minus PV, so this minus this, so that gives 98883 Newton per meter square. So that is 98,883 Newton per meter square. So this you can see from here, specific humidity at 20 degrees Celsius. So omega s equal to, we know this equation, we have seen already to find out specific humidity. So that is 0.622 into PV by PA. So we know the PA is 2342, and PV is 2342, and PV is 988. That is PA is 998,883 Newton per meter square. So after solving this, we are getting omega s, that is specific humidity, 0.01472 kg of water vapor per kg of dry air. So from here you can see this is the TS diagram, as steam diagram, steam tables, you can see this, and this is the condition where the condition water vapor at 20 degree Celsius saturation, and this is the PS equal to PA. So this is the 20 degree Celsius, and we can find out these parameters in TS diagram. And now we will move to the psychrometric chart. At 20 degrees Celsius, on temperature, where dry bulb temperature, we have the specific humidity 0.01472. Now this is the intersecting point A. So use of this chart, knowing T and omega s, point A can be plotted. So point A is now is known as intersection point. Similarly, the saturated states, at other temperatures can be used to plot saturation line. So once we know a point, so we can find out other parameters, and saturation states, if we come to know all other parameters, very easily we can extract from psychrometric chart, and this forms the backbone of psychrometric chart. So this point, finding the point is very important. The intersection point, once we find the rest of the things will be very simple. So relative humidity lines. So relative humidity lines, already we have seen it is in terms of percentage, and here relative humidity is the ratio of actual vapor pressure to saturation pressure of water vapor at the same temperature. Already we discussed this. Now we are revisiting that. And the psychrometric chart, the 100% relative humidity line is the saturation curve. So the saturation curve that we have seen on the left hand side, so that is known as the saturation curve, and 100 percentage of humidity you can find there, and that separates both states. RH relative humidity lines of other values, example 50 percentage, are drawn using intersection of PV at known T, and example 50 percentage of RH at 20 degrees Celsius from steam tables. So PS can be find out. So that is for 50 percentage of RH at 20 degrees Celsius, it is 2342 Newton per meter square, and PV equal to 0.5 into 2342. So that is coming as 1171 Newton per meter square. So PA also can be find out. So it is 101325 minus this is the PS. So this is 1171. So it is coming around 1 lakh 154 Newton per meter square. So omega can be find out here. So 0.622 divided by into 1171 divided by 1 lakh 154. So it is coming as the 0.00727 kg of water vapor per kg of dry air. So using these values, the point C in figure can be plotted. So now the point C can be plotted. So this is the point C in plotted. Repeating for other temperatures gives the full RH line. So now this is the relative humidity line, and now we are plotting point C, and where we can see, we can find out this 0.00727. So that from here we are finding out the point C. So against 20 degree dry bulb temperature, and the specific heat, that is point specific humidity, so that is relative humidity, we are finding out here. So it is on 50 percentage of RH line. So this is the simple way to find out the intersecting points. So drawing 50% of RH line. So constant specific volume lines. So constant specific volume lines we have seen in main diagram. Now we will see in detail. So drawing of 0.85 meter cube per kg of dry air, constant volume lines. So this is the constant volume line. So this is the point B. So this is the constant volume line. This is constant volume line, and on this 0.085 meter cube per kg of dry air. So this is the intersecting line for this relative humidity is at 25 degrees Celsius of dry bulb temperature. It becomes point B. So to draw the dry line corresponding to specific volume 0.85 meter cube per kg of dry air, so proceed with the trial and error method first. So then step by step we can see the point A is dry bulb temperature is 20 degrees Celsius. So this is the point A, and then PV equal to 2342. So that is equal to PA. So PA we can find out here. So it is 98883 Newton per meter square. Now VA is RA by T by PA. So that is 287.3 into 273 plus 20 divided by the PV, so that is PA or PV, both are same. So now this comes as 0.85 meter cube of kg of dry air. So this is the line, and omega is equal to, we can find out omega, that is 0.1472 kg per kg of dry air. So point B, that is the dry bulb temperature 25 degrees Celsius. So PA for point B is equal to 100727, so that is Newton per meter square, and PV is equal to 601 Newton per meter square. So omega is 0.00597, so that is the 0.00597 kg per kg of dry air. So these points A and B define the constant specific volume lines. So this is the point A, and B through point A through B if you draw, and it will meet the dry bulb temperature at C. So constant thermodynamic wet bulb temperature lines. So these are the wet bulb temperature lines. So this the vertical, inclined line is known as constant wet bulb temperature lines. So for 20 degrees Celsius constant wet bulb temperature line, so the adiabatic saturation process using the energy equation, so that is H equal to the omega star minus omega HF dash equal to H star. So the sigma equal to H minus W HF dash, so that is equal to H star minus omega star HF dash, so that is equal to constant. And example, you can see WBT equal to 20 degree Celsius, so that is the wet bulb temperature is 20 degree Celsius. So for 20 degrees Celsius, so we are marking a point here, and this is the wet bulb temperature line, and this 20 degree we are measuring from dry bulb temperature, and point A on saturation curve, so that is the omega star equal to 0.1472 kg of kg dry air. So this is the omega star, and this meets at point A on saturation line. So H star equal to, that is 57.47 kg kilojoules per kg of kilojoules per kg. So sigma can be find out, so that is H dash H star minus omega star HF, so that is coming as 56.21 kilojoules per kg. And point B, dry bulb temperature is 30 degrees Celsius, so same, now we have to repeat that, and omega can be find out by using sigma, and this is the equation, and we are finding out the omega value as the 0.01072 kg of kg dry air. So H equal to enthalpy equal to sigma plus omega H dash F. So that is 56.21 plus this omega. So into HF. So HF is 83.9. So 83.9. So it is coming as 57.11 kilojoules per kg. So multiple such points plotted across DBT. So we can plot any number of points, and where we, with sufficient data, when data is available, we can plot a number of points. So DBT values will yield the constant wet bulb temperature line. Example, so 20 degrees Celsius wet bulb temperature. Next line is constant enthalpy lines. So this is the constant enthalpy line, and now with the available data, by extending the points to this line at 90 degrees, we will get constant enthalpy values. And from earlier calculations, the difference between enthalpies at saturation point A and B point on the same constant wet bulb line is very small. So this difference is termed as enthalpy deviation D. So this is the D and this is minus 0.34. So this deviation is known as enthalpy deviation, and D equal to H minus H star. So that is equal to omega minus omega star HF star. So in this example, same example, so D is equal to 57.11 minus 57.44. So that is 0.34. So 0.34 minus 0.34 kilojoules per kg of dry air. So thus the enthalpy scale only gives values for saturation points. For other points on constant wet bulb lines, so H equal to H star plus D. So this enthalpy equation can be used to find the H. So now we will see psychrometric charts for low and high temperatures and high altitudes. So that is the from sea level, and the height above MSL, that is the mean sea level in terms of meters. So sea level is 0. Above that we have 1520, 2280 and 2750, and these are the examples we are taking. And the corresponding barometric pressure at sea level, it is 760 millimeter of Hg, and at 1520 it is 693 millimeter of Hg. At when it is when the altitude increases, the barometric pressure is getting reduced. So that is 12750 meters above the sea level, then it is 577 only. The standard psychrometric chart is valid for DBT. So dry bulb temperature ranges from 0 degrees Celsius to 50 degrees Celsius only, and the humidity ratio is 0 to 0.03 kg of water vapor per kg of dry air. And other charts are created for the sub-zero temperatures used in winter heating and high temperatures for dry process calculations, and these are the other charts available. And in sub-zero conditions, the latent heat is based on sublimation, so it is not vaporization. And effect of altitude, so barometric pressure decreases with height as shown in table, and psychrometric charts must be recalibrated for each altitude. So psychrometric chart, so for depending on the height or altitude, the psychrometric chart should be drawn or should be determined. So coming to the application of first law of psychrometric process, you can see a psychrometric process involves change of state of moist air. So common processes: cooling, heating, humidifying and humidifying. The summer air conditioning uses cooling and dehumidifying, and winter air conditioning uses heating and humidifying. So thermodynamic analysis use the steady state steady flow. So that is SSF energy equation, and the key parameters involved here are specific volume, enthalpy, specific humidity. So these are either calculated analytically or obtained from psychrometric charts. So we can calculate analytically also, but psychrometric charts are always available. We can make use of psychrometric charts. So example, cooling and dehumidification of moist air. So the given is moist air at saturated atmospheric pressure is passed over a cooling coil. So the inlet and exit states are given in this table. So that is the first number state. So that is inlet state. So dBT and relative humidity is given. So 30 degrees Celsius and 50 percentage. At exit it is 15 degree dry bulb temperature, and RH, that is relative humidity, is 80 percentage. And fine, show the process on a psychrometric chart. Determine the amount of heat and moisture removed per kg of dry air. So this is the cooling coil schematic. So this is the cooling coil schematic, and the moist air in, so that is 25 degrees Celsius and 50 degree RH, and moist air out, so that is 15 degree Celsius, 90% of RH. So this is condensed moistures at 8 degrees Celsius. So this is cooling coil. So water vapor refrigerant out, and this is the vapor liquid refrigerant in. So after cooling, it is vapor refrigerant out is taking place. So this is the cooling coil schematic, and the next is cooling and dehumidification process on psychrometric chart. So this is the psychrometric chart, and this is the dry bulb temperatures, and for 10 degree it is point S, and it is 15 degree it is S. So this is the 90 degree 90% of relative humidity, and this is 100% relative humidity. It is also known as saturation line, and this is the point 1 for 50% of relative humidity, that comes as 30 degrees Celsius, 30 degrees Celsius. And now this is the cooling and dehumidification process on psychrometric chart for the given problem. So applying continuity equation, and we can see MA equal to MA1, that is equal to MA2. So MW3 equal to MA into omega 1 minus omega 2, and the energy equation triple SF equation Q plus MA H1 plus MA omega 1 HV1, so that is equal to MA H2 plus MA W2 HV2 plus M omega 3 and MW3 and HW3. So dividing by MA, so we are getting Q equal to H2 minus H1 plus omega 2 HV2 minus, and omega 1 HV1 plus omega 1 minus omega 2, that is HW3 is multiplied. So step 1, saturation pressures from steam tables we have to find. So always keep steam tables with you, and P dash V1, so that is 30 degrees Celsius equal to 4.246 kilopascal. So PV2 is at 15 degrees Celsius, it is 1.7051 kilopascal. So P1, and we can PV1 is multiplied by 0.5, so into 4.246, so that is 2.123 kPa, and PV2 is 0.8 in 0.8 into 1.7051, so that becomes 1.3641 kilopascals. So this is the first step. And then step 2, specific humidities we have to find. So from this equation, already we know this equation, omega 1 equal to 0.622 into 2.123 divided by 101.325 minus 2.123, so that is 0.01331 kg of water vapor per kg of dry air. So omega 2 also can be found out from the same equation, and it is coming as 0.00849 kg of water vapor per kg of dry air. So step 3, specific enthalpies. From steam tables we can find HV1, HV2 as well as HW3. So step 4, applying energy equation. So just substituting all these values in our energy equation, we are getting Q equal to minus 27.3 kilojoules per kg of dry air. So for this given example, it is minus 27.3 kilojoules per kg of dry air. So final result is moisture removed per kg of dry air. So that is equal to omega 1 minus omega 2. So it is 0.00482 kg of per kg of dry air. And heat removed from moist air Q equal to minus 27.3 kilojoules per kg of dry air. So process is plotted from point 1 to point 2 on figure. So in the earlier figure I have shown you. and you can see the textbooks. CP Arora you can refer for this topic, and we have other books, Rajput and Kurmi. You can refer these books for additional information. And numerical problems, number of problems you can find in Kurmi as well as in Rajput. So please practice those numerical problems for exam point of view. So these are the other resources we have, and we stop here, and we will meet again in next session, students. So for any clarifications, feel free to contact me. So thank you, students. We stop here. We will meet again in next session. Thank you, students.